Good afternoon, dear colleagues. So now in the end of this session of carbonation, I will give a presentation on carbonation of concrete. So one comparative study between alkali activated concrete and cement-based concrete. So to give a brief outline of the presentation, so I will say something about the background, the materials and methods, some results and the conclusions. The differences, first of all, between cement and alkali activated concrete um, are mainly in the binder type that is used, and geopolymer concrete does not use any cement. The reason why we are studying so much alkali activated materials in general is that it it gives so much potential for reuse of resources, of primary resources, and and there are no standards, there are no guidelines how we can actually implement these materials in the practice. In this presentation, I will mainly talk about carbonation in terms of the service life performance. So there are two main degradation mechanisms, let's say major, when it comes to the end of the service life of the concrete, and those are carbonation and chloride ingress. We are interested today only in carbonation, and as you can see, carbonation mainly leads to pH reduction and to the global loss of passivity of the steel reinforcement in concrete. However, is this the case also in alkali activated concrete? So this is what is known for cement-based concrete. So I will present strength development of alkali activated concrete compared to cement concrete. Then some results on characterization of the carbonation front, propagation, and the pH of these concrete ones when they are carbonated. So in the mixture proportions, we can see, so there are four concrete mixtures. Each of them has a amount of binder of 4 kilos per cubic meter. Then the aggregate distribution and amounts were same for all mixtures, and also the liquid to binder ratios were 0.5, with exception for mix 2 S50, where it was 0.6. In exposure conditions, there were three types that are studied. So laboratory carbonation, natural indoor, and natural outdoor. For them, the conditions are specified in the table below and also in the paper. So now, when it comes to results, what we first can see here is that the strength is studied from for a period of 548 days, and as you can see, the strength is developing also after 28 days. Now I will point as well. So here we had a curing, so prior the carbonation for 20 days, then preconditioning, and then we had exposure to carbonation from day 56. The strength of alkali activated concrete in this study are higher, and you can see how much here. Why is that? So once when we basically look, 7 days of alkali activated concrete corresponds to 28 days of the cement based concrete. Namely, the macrostructure differences are very important for these two types of concrete. So for alkali activated, for instance, slag, the microstructure is so well developed, or let's say so dense at 28 days, while in OPC, or let's say in ordinary Portland cement paste, there are still so many porous spaces where the cement hydration is still continuing. When it comes to carbonation evaluation, so as you can see, there were, let's say here, 5 samples. So I added also one on a fiber reinforced geopolymer concrete. As you can see, this was before spraying with phenolphthalein, so the second row and the third one is after spraying the phenolphthalein. So the phenolphthalein indicator is not the best indicator for carbonation front in alkali activated materials. And because of that, since you can see here, the front is basically very close to the border, while in once, let's say after spraying the phenolphthalein, that border moves much lower. And because of that, we investigated also the carbonation front with a microscopy. So under the cross-polarized light, we could observe the zone, or let's say the front between carbonated part and non-carbonated part. So non-carbonated part and carbonated part. And as you can see in the non-carbonated area, the microstructure is black because it's amorphous, while in the carbonation area, the microstructure is full of light small calcium carbonates. Further, the propagation of the carbonation front for this period of 548 days. So what we can see is that in a laboratory conditions, the rate is similar to one outdoor, let's say indoor or outdoor, compared to the accelerated carbonation at 1% CO2. So there, in a mixture of S50 0.6, it propagates up to 35 millimeter compared to, let's say, 5 millimeter in ordinary Portland cement. So why? Yeah, of course, the question is why. So we know that the carbonation mainly induces drop of the alkalinity in the pore water of the concrete. And here you can see for the accelerated carbonation. So once we had the carbonated layer of 35 millimeter, the pH was evaluated basically on every 5 millimeter from the top surface by grinding and dissolving it and then testing the alkalinity. And we can see that on the very top surface, the lowest alkalinity is actually in a alkali activated concrete, whereas for cement, cement 1, it's higher, while for cement 3B is even lower than for alkali activated concrete. When we look for natural indoor and natural outdoor, they all are above 9. The pH is above 9, and yeah, it actually slowly drops and it stays high in the really inner part of the concrete. So there are two, let's say, main reactions which are happening when alkali activated concrete carbonates. First of all, the carbonation of the pore water with all alkalis that are inside together with CO2 molecules, where we have formation of the sodium or of the bicarbonates or carbon of sodium carbonates. Then we have also formation of the calcium carbonates if there is, of course, a source of the calcium oxide in the matrix. We also should note that on these graphs, the pH is presenting not on a logarithmic scale. So there is a huge difference, let's say, between 9 and 10, or 12.5 and 13.5, like here is pointed out, because that means 10 times higher OH minus concentration. And then to go further to explain, although the compressive strength of alkali activated materials is so high at 20 days and the microstructure is so dense compared to SEM1 concrete and SEM3B, and even the porosity is consequently also much lower than compared to porosity of SEM1 and SEM3B. The calcium hydroxide makes a huge difference, and also the amount of calcium oxide that is inside the matrix of SEM1 and SEM3B. That consequently means that the CO2 binding capacity is much higher for SEM1 and SEM3B. So that means that for CO2 or for carbonation, it's longer time to carbonate available calcium oxide, while for alkali activated materials, since they have a low calcium oxide content, then also consequently CO2 binding capacity is lower, and then carbonation can propagate faster. So more details about this you can find in my PhD thesis. So the main consequences of carbonation between cement and alkali activated concrete are drop of pH and the change of the pore structure, and which is actually occurring for alkali activated concrete much faster because they have a lower calcium oxide content. Some guidelines for preliminary design for concrete where it would be, let's say, exposed to the carbonation. So it is very important to use to use raw materials which have a high amount of calcium oxide in its composition. This really offers increased decarbonation resistance. And alkaline activator, it's very important in the mix design when that the sodium oxide is balanced, so that eventual leaching from the surface of alkali activated concrete during curing is not happening. Curing methods, so curing at lower relative humidity than 80% would hinder alkali loss, or let's say leaching from the alkali activated concrete. So curing compound is absolutely necessary. And curing at higher relative humidity leads inevitably to alkali loss. This is also something that you can in detail see in my thesis. And exposure conditions, so the exposure of alkali activated concrete to permanently wet or long-term water contact should be avoided due to potential alkali loss, unless the mix is so good designed that actually alkali loss is avoided. Thank you for your attention, and I will be very glad to answer your questions.